Hello guys, welcome back to my channel. Today we're going to be looking at the concept of complex number, but we're going to start with a little experiment which you're going to look at and try to see what is wrong with it before I'm complete. So let us go ahead. We're going to be using the law of equality to say that A is equal to A. Now with that concept we can actually say that 1 is equal to 1. However, I could write 1 as 1 times 1. And bear in mind that 1 is also the multiplicative identity. I could write 1 also as -1 times -1. But whenever we multiply a number by itself, as a shortcut, we could use it as a square. So I could write the left-hand side as 1 square, and I could write the right-hand side as -1 squared. Now, what if I were to take the square root of both sides? So I would have the square root of 1 square equal the square root of -1 squared. Now, by laws of surds, we can actually say that the square root of a squared is actually equivalent to the root of a all squared, which we all normally say is also equivalent to a. So, looking at the left-hand side, the square root of 1 square could be written as the square root of 1 all squared, which I could also write the right-hand side as the square root of -1 all squared. Now, when I square the square root, I'm going to end up with 1, and I'm going to have on the right-hand side, the square cancels out the square root, so I end up with -1. So here I have that 1 is equal to -1, but we know, of course, that this is not true. Now, why is this not true? All of these operations that we carried out, we assume that we were operating in the real number system. However, here is the problem. The square root of -1 is not a part of the real number system. So the root of -1 is not a member of the real number system. So that is why this operation would totally be illegal. The square root of -1 falls into another number system that is referred to as a complex number system. And normally we use a capital C to represent the system. So the square root of -1 is a member of what we call a complex number system. Now, in this number system, the square root of -1 is represented as I, sometimes we might use J. So to clarify this, we're going to be building up the number systems from start to finish. So let's start with the simplest kind of number system. At the beginning, the simplest number system we have is what we call a natural number system. We also call the system the set of counting numbers. So we have 1, 2, 3, and this goes all the way up to infinity. Then we have the set of whole numbers. And the only difference between natural numbers and whole numbers is that whole numbers does include 0. Once we have the whole numbers, we have what we call a set of integers, generally represented by Z. Now, of course, the set of integers includes now negative numbers, so it includes the natural whole numbers, all the whole numbers and natural numbers. It also includes the set of negative numbers as well. Now, once we have established that, the next system that we look at is what we call a set of rational numbers. And generally, we can go ahead and represent that system by Q. There's no fixed symbol for it. Now, the set of rational numbers are numbers that can be expressed as fractions, such as a half, a quarter, and so on. We also have the set of irrational numbers. And for that set, I'm going to be using Q prime. Now, irrational numbers are numbers that can be expressed as a fraction. And we're looking at things like the square root of 2, root 3, root 5, e especially, and pi. And let me put those two special ones in there, e and pi. Those are what make up the set of irrational numbers. But all of these number systems, rational and irrational, come together to form what we call the real number system. They're all a part of the real number system. And that is as far as you probably would have gone. But now we're introducing you to a larger system. all of these are part of a larger system, and this system is what we refer to as a set of complex numbers. Now, the set of complex numbers would of course take in things like the root of -1, which we say is generally represented by I, which means imaginary, of course. So we are venturing into the imaginary realm at this moment. And we're going to be looking at some basic operations with I, because if the square root of -1 is I and we're inside of a complex number system, then we need to understand how this works. So we're saying that the square root of -1 is represented as I, which means that I can say the square root of -1 squared is equal to I squared. Now, here the square would actually cancel the square root, so I'm going to have -1 is equal to I squared. Now, let us take this a bit further. What if we were to multiply both sides by I? So I would have -1 times I is equal to I squared times I. So -I would be equal to I cubed. All right, let's go again. What if I go again, take the same thing and I multiply both sides by I again? So I'm going to have -I times I is equal to I cubed multiplied by I. I would have -I squared equal I to the 4. Now, we know already that I squared was equal to -1. So I would have negative of -1 equal I to the 4, which means I to the 4 is equal to +1. Now, with these three things, we can find I to any power. So let me highlight them. We know that the square root of -1 is equivalent to I. We know that I squared is equivalent to -1. We know that I cubed is equivalent to -I. And we know that I to the 4 is equivalent to 1. So the question is, what if I had asked you to find, let me get some space here. What if we wanted I to the, probably I to the 400? Now, what I would simply need to do is to write I to any one of these powers here. Now, of course, we know that 400 is definitely divisible by 4. So by laws of indices, I could actually write this as I to the 4 raised to 100. Now, we know that I to the 4 here is +1. So what I would end up with is 1 to the 100, which of course 1 raised to any power is still +1. Now, of course, that was pretty straightforward. Let me get a different example. What if I wanted I raised to the 19 power? Now, of course, 19 is not divisible by 4, but guess what? I could find the closest power to this that is divisible by 4, and in this case, it would have been 16. So I could write this as I to the 16, and of course, 19 minus 16 is 3, so times I to the 3rd power. Now, I to the 16, of course, we can go I to the 4 raised to the 4. What about I cubed? Now, if we go back up, we would have found out that I cubed was equal to -I. So to simplify this, this becomes times -I, and of course, I to the 4 is 1, so we have 1 to the 4 times -I. But once again, 1 raised to any power is 1, so you have 1 times -I, which becomes -I. And that's my answer. So we can practically take any power and break it down. The only tools we need are that I squared equal -1, I cubed equal -I, and I to the 4 equal 1. All right. So we try to find the closest power that is divisible by 4. For instance, taking 19, I know that the closest thing to that divisible by 4 is 16. And then by using laws of indices, I rewrite I to the 19 as I to the 16 times I cubed. Now let us look at the parts of a complex number. Generally, a complex number has two parts, and a complex number normally takes the form z equal x plus iy. So the complex number has two parts, the real part and the imaginary part. Now the real part is normally represented as short re. So let us say that the complex number is represented by z. I would say that the real part of z is equal to x. The imaginary part, normally shortened imz, is a coefficient of the I, which in this case is y. So the I is not a part of the imaginary part, it is the coefficient that forms the imaginary part. Now let us look at several examples. What if we have z equal 4 plus 6i? The real part of z would be equal to 4, but the imaginary part of z would be equal to 6. Let us look at the next example. What if it was z equal negative 6i? What would be the real part of z? Now clearly, we're not seeing that part, which means it has to be 0. The imaginary part, we can see is the coefficient of the I, which is equal to negative 6. So clearly we can see that. Now let us look at a more complicated example. Now, what if I had 2 plus 3i squared minus 4i? What would be the real part? Now, clearly, because we have powers higher than I, we have to simplify it. So we can actually recall. So recall, earlier we had said that I squared is equal to negative 1. So this actually becomes 2 plus 3 times negative 1 minus 4i. So you can see here that the I squared, 3i squared, is actually a part of the real part, because when you simplify that, it becomes real. So what we have here is 2 minus 3 minus 4i, which becomes negative 1 minus 4i. So the real part is equal to negative 1, and the imaginary part is equal to negative 4. Now we're going to be looking at addition and subtraction of complex numbers. Now, of course, we can think of this like vectors because it has two parts, the real part and the imaginary part. So let us say that we have two complex numbers. Let me call it z1 equal a plus ib. Let me say that z2 equal c plus id. Now notice that we can either write it as ib or bi. It means the same thing, right? What if we want z1 plus z2? This would imply a plus ib plus c plus id. So I'm going to be looking for what we call like terms. That is how addition and subtraction works. Now, in this concept, the like terms must be the real parts and the imaginary parts to themselves. So in this part, my real parts are a and c. So I would have gone a plus c, plus my imaginary part was ib and id. And of course, since we have ib in common, we can factor that out. So we have b plus d, and we have the I there. So clearly, my imaginary part is b plus d, and my real part is a plus c. Likewise, if I wanted z1 minus z2, the concept pretty much would be the same. You would have a plus ib minus, and of course I put that in a bracket, c plus id. So when I clear the bracket, I would end up with a minus c of course, as my real part, plus, once again, realize it's going to be a minus. So we're going to look at an example of addition and subtraction of complex numbers. So let us start with A. A says that we have Z plus W. Now Z is equal to negative 7 plus 4i, and W is equal to negative 12 minus 8i. So what I have is negative 7 plus 4i being added to negative 12 minus 8i. All right, let us clear the brackets. So we have negative 7 plus 4i. Well, here we have a plus, and once you add a negative, it becomes a minus. So it's minus 12 minus 8i. Now, looking for the real parts. The real parts here would be negative 7 and minus 12. And we're going to have plus 4i minus 8i. And we simply just break this down. So we have negative 7 minus 12, which is going to be negative 19. And then we have 4i minus 8i, which is going to be a negative 4i. So clearly, the real part is negative 19, and the imaginary part is negative 4. Let us look at B. Now, with a minus, you have to be very careful. So this is in particularly where the brackets become very useful. So I'm going to have negative 7 plus 4i. I don't necessarily need to put that in a bracket, but I'm subtracting all of W, so that must go inside of a bracket. So we have a negative 12 minus 8i. This becomes negative 7 plus 4i. Now, if we clear this bracket, since what is inside of the bracket is negative, and we have a negative outside of the bracket, everything becomes negative. So I'm going to end up with a 12 plus 8i. We'll do the grouping as well. The real part would be negative 7 plus 12. And then we have plus 4i plus 8i. Now this becomes 5 plus, 4i plus 8i was going to give me 12i. So my real part is 5 and my imaginary part is 12. We're now going to turn our eyes to the equality of complex numbers. Now let us say we have two complex numbers, z1 which is equal to a plus ib and z2 which is equal to x plus iy. Now let us say that z1 is equal to z2. This would imply that a plus ib would be equal to x plus iy. Now, when comparing these two things, we're going to have to compare similar parts. So we have to compare real parts and we have to compare imaginary parts. Now, on the left, my real part is a, and on the right, my real part is x. So if this is true, and let me change the color here. If these complex numbers are really true, this would imply that a must be equal to x and that b must be equal to y. So the real parts are equal and the imaginary parts are also equal. Now, by just looking at this, we have two different equations here, which tells me that this could be grounds for solving a simultaneous equation. So here we're given a scenario that 2 times a plus ib plus 3 times a minus, and of course there should be ib, equal 5 minus 2i. And my job is to find a and b. Now, of course, we say that when two complex numbers are equal, the real parts are equal and the imaginary parts are equal. So my task here is to find out what is the real part on the left, what is the imaginary part, what is it on the right, and what is the imaginary part on the right, and just to equate them. But we're going to have to do some tidying up first. So let us go ahead and start by expanding the brackets. So we have 2a plus 2bi, and of course I could put the I at the front, I2b, it doesn't matter, plus 3a minus 3bi equal 5 minus 2i. Now on my left, my real parts would be 2a and 3a, and my imaginary parts would be 2b. So we have 2bi there, and we have minus 3bi, which is equal to 5 minus 2i. Now, we know that 2a plus 3a is actually equal to 5a. And 2bi minus 3bi, of course, is going to be minus bi. equal 5 minus 2i. So the real part on the left would be, so I could say this implies that 5a is equal to the real part on the right, which is 5, and the imaginary part on the left is minus b, and the imaginary part on the right is minus 2. So this implies that a is equal to 1 and b is equal to 2. Right? And this is probably the simplest you could actually get a question. All right, as we go along, we might look at more difficult questions. Now we're going to be looking at the multiplication and division of complex numbers. So let's say we have two complex numbers, z equal x plus iy and w equal a plus ib. Now what if I want z times w, which I could just write as zw? This would imply x plus iy times a plus ib. So normally when expanding brackets, we know we multiply everything in the first bracket by everything in the second bracket. So I would have x multiplied by a, which would give me ax, keeping it alphabetical, then x times ib. So probably I could write that as ibx, right? And of course we don't want to put the I in between because the b and the x are components of the I. Plus, you're going to have iy times a, so I could say I ay, and then you're going to have iy times ib. So I'm going to have I squared by. But from previous lessons, I would have known, and let me change the color here. So recall, we know that I squared is equivalent to -1. So this expression is going to become, and we can start grouping as well. So I'm going to have ax plus ibx plus iay. The I square we said is equivalent to -1, so we have minus by. So my real parts would be ax minus by, and we're going to have plus, let me just factor out the I here, so we have bx plus ay. So clearly we can see that the real part is ax minus by, and the imaginary part is bx plus ay. And that is how we pretty much go about multiplying two complex numbers. But under multiplication, there's something interesting that we want to look at. Now let us say we say that z equal x plus iy, and let us say we have, there's a special name for what I'm going to do, but I'm not going to point it out as it. What if we want x plus iy times x minus iy? Now, of course, we know that there are several ways to approach this. We would have actually recognized this as the difference of two squares. So I could go x squared minus iy squared. Now by laws of indices, this becomes x squared minus I squared y squared. Now I squared is -1 as we just saw, so we have x squared minus -1 times y squared, which becomes x squared plus y squared. Notice that in this expression here, we have no imaginary parts. X squared plus y squared is real. Now, let us go again, and this time I'm going to have x plus iy, and I'm going to add it to x minus iy. So I'm going to have x plus iy plus x minus iy. Now, looking at this, x plus x is 2x, and iy minus iy is going to give me 0. There's a special name given to this set. So if we say that z equal to x plus iy, x minus iy is what we call the conjugate. So this is called the conjugate, conjugate. Now already you can see how useful the conjugate is, because when we multiply a complex number by its conjugate, then it automatically becomes real. If we add a complex number to its conjugate, we have 2 times the real part. And let me highlight these two things here and here. Now there's a special symbol that we use for the conjugate. The conjugate can either be z bar. So if z is a complex number, the conjugate z bar is x minus iy. Or you have z with an asterisk, which is also equal to x minus iy. This in particular is very useful, right? All right, here's a typical question now where I'm actually looking at multiplying complex numbers, but I also have the concept of equality here. So find the values of x and y. So I'm going to start by breaking it down so we can actually compare the complex numbers. So let me just create some space here. So we have 3 minus 2i times x plus iy equals 16 plus I. As we said earlier, in order to compare the real part and the imaginary part, I must distinctively be seeing the real part. So let me go right ahead. So everything in the first bracket will multiply everything in the second bracket. Oh, so we go ahead with 3 times x, which is going to be 3x, and 3 times iy. So that's going to be plus I 3y, or we could say 3yi, whichever one works. Then we have minus 2i times x, so it's minus I 2x. Then you have 2i times iy. So that's going to give me minus I squared 2y. This is equal to 16 plus 11i. Now bear in mind that I squared is equal to negative 1. So we're going to have 3x plus I 3y minus I 2x. And then of course if I squared is negative 1, and we already have a negative here, it becomes plus 2y equals 16 plus 11i. Now, can I figure out what the real part is? Yes, we have 3x and 2y. So we can say this implies that 3x plus 2y is equal to 16. Can I figure out what the imaginary part is? We look for the i's. So the imaginary part is a component of the I. So we have 3y and we have minus 2x. So you have 3y minus 2x. And on the right hand side, the imaginary part is 11. So here we have a simultaneous equation. So I'm lining them. So I have 3x plus 2y equals 16. And we're going to have minus 2x plus 3y equal 11. So we can probably multiply equation 1 by 2, so times 2. And we could multiply equation 2 by 3. So this becomes 6x plus 4y equal 32. And if we multiply equation 2 by 3, we have minus 6x plus 9y equal 33. And we'll go right ahead and add these equations. So 6 plus minus 6, that's 0. Then we have 9 plus 4, that's 13y equals 65, which will of course imply that y is equal to 5. Now we can substitute this in any one of the equations. So probably I could sub it in the first equation, which is 3x plus 2y equals 16. So I'm going to have 3x plus 2 times 5 equals 16. So 3x equal 10. Well, no. This will be 3x equal 16 minus 10. So 3x equal 6, x equal 2. So therefore, x equal 2 and y equal 5, right? Pretty much we tying in multiplication of complex numbers with equality of complex numbers.